this is a chapel in Prague, in the Czech Republic, that was built a long time ago in the Baroque period. And that's where we're going to find out what we're talking about today. Okay, let's go in. The subject today is chirality. That comes from a Greek word, chair, which means hand. And that's where the word surgery comes from. Because surgery is people who work on you with their hands instead of giving you medicine. But we're talking about chirality, which was a word that was thought up about 100 years ago by a guy named Lord Kelvin. And it has to do with hands, with handedness. It involves things which are mirror images of one another, like your two hands, but are not superimposable. They're not identical. They're obviously very, very similar to one another, but they're not the same thing. And they occur all kinds of places. For example, in art and architecture, you can see that this column on the left has a spiral on it, and it's a right-handed screw, but the one on the right side, unfortunately, is a left-handed screw. Right? But it's not only in art and architecture that you see mirror images like this. Also in biochemistry. Have you ever seen this stuff? Does anybody know what it is? Yeah, what is it? DNA, right. And so here we have one that's spiraling one way, and over there we have one that's spiraling the other way. And it happens in molecules too, which organic chemists like me work with. Like sugars and carbohydrates are right and left-handed. Amino acids and proteins, the stuff that make you, are right and left-handed. The molecules of life on Earth are what's called homochiral. That is, they're all the same hand. Right? So for example, you only have the right-handed screw of DNA with you, not the left-handed screw. And you only have the L-serine amino acid, and you only have the right-handed glucose in you. Now this raises some questions. The first one is why? Why not have both? Well, there's some pretty easy explanations for why that. One is recognition. Let's see, do you ever shake hands with people? Here, let's shake hands. Shake hands with your neighbor, but one of you put out the left hand. That feels really funny, right? The right hand feels different. So it makes a difference which hand you use if you're interacting with something else that's a certain hand, right? And molecules in biology interact with one another, so they have to be the proper hand to interact correctly. So that's recognition. Also, efficiency. If in doing your biology, you're only going to use one hand, you don't want to waste a lot of your food making the wrong stuff and have to throw it away. Right? So it's much more efficient to deal with just one hand. Now, sometimes you do have both hands, like these things that are called essential oils. They're called essential not because you need them, but because they have an essence, they have a smell. Right? So carbone is a compound that comes in both hands, and there are little vials going around which you can open up and smell if you want of them. And one of them is the R-carbone, one hand, and that is spearmint. And the other one, the left-handed carbone, is caraway or dill seed or rye bread. Okay. So sometimes you use both, but almost always biology uses only one, and when it uses both, it uses them for different purposes, like being rye bread or being spearmint. Okay. Also, the shape of a polymer. You know, it's really important to have this helix of DNA. And every molecule is the same hand as you go around the helix. If suddenly you put in the wrong hand, it would go a different way and then another way, and it would get all messed up and your DNA wouldn't work at all if it were a mixture of hands. So that's why biology deals with just one hand, why biology is homochiral. Now there's an interesting question. When? When did life become homochiral? It's like the question of the chicken and the egg. Which one came first? It's the question of life and hand. we can't imagine life without all things being the same hand nowadays. Right? So, but the way we get single hands is from life. So which one came first, the life or the hand? It's not obvious. And in either case, there's the question of how. How was the original selection made to get just one hand? And which? I think any chemist you talk to, or biologist, will say that if all of us became our mirror image, and the whole biosphere, all trees and bacteria and everything, were their mirror image, everything would work just fine. But we're all one way. What decided which one we would be? Okay, so the title that got you here was Did Life Grind to a Start? And you can imagine early life living on a beach where sand and waves would grind things up. Okay? Now, chemists, especially chemists of a certain age, get interested sometimes in how life began. And there is, for example, this story in the New York Times a few years ago as a chemist shows how RNA can be the starting point for life. This is a guy named John Sutherland who teaches at Cambridge in England now. And so he's studied how the molecules can begin, but not the part about which hand it is. Right? I'm not going to talk about the type of stuff he did. Right? What I'm going to talk about is a brief history of the origin of homochirality. How could things have become one hand before life? Not that I really know that they did become one hand before life, but that's the chicken and the egg thing. Is there any way it could have become one hand before there was life to control it? Now, of course, nobody knows that. And nobody is really likely to know that, I don't think. So I really, and for example, Francis Jack in 1898, and we'll talk about him a little later, said the absolute origin of compounds of one-sided asymmetry to be found in the living world is a mystery, as profound as the absolute origin of life itself. Right? Unfortunately, for me, it's still a mystery, right? The origin of life. So I'm not, and how homochirality began, I don't know. So I'm not even going to talk about that. What I'm going to talk is a brief history of some ideas about the origin of homochirality, and we're going to start way back when, and we're going to go in steps of about 50 years to see the ideas people had. So it all starts, as you'll see how it's related to the idea of polarized light. How many of you have ever interacted with polarized light? How many of you ever wore sunglasses? You've interacted with polarized light, if they're good sunglasses. So let me show you here. This is, this guy, Malus, was interested in was what is the nature of light? Right? And a discovery he made was that light can be polarized. So I have here a filter that lets just one kind of light through. And here you can see that light comes through, and here it doesn't. Right? And the idea here is that light, which we now know, which he didn't know, is vibration of electrical field. So electrons vibrate, and they make an electric field that goes back and forth. Right? But it goes all different directions, back and forth. This way, one electron's going this way, one's going this way, one's going this way. So all different directions. But if you put, then that makes waves coming to you as the light comes to you, up and down, back and forth, back and forth. But if you had a picket fence there, only the waves that are going the same direction as the slats of the fence can get through it, not the ones that are going this way. And that's what this stuff does. So that showed that light had an aspect about it like waves, right? So that's like a picket fence one way, and here's the picket fence the other way, and as we turn it, if the two sets of picket fence are the same, the light will come on through. But if one's perpendicular to the other one, it'll stop it. So we see that. Okay, that's what Malus did. He discovered polarized light. But now there's some funny things about polarized light. So let's see what happens if we put a piece of glass there. Right? And we take this, and it's just, the glass is no different from the light that doesn't go through the glass, right? Well, let's put something in there, like let's take my water and dump it in there. Oops. Okay, and we'll try again. And water doesn't do anything. Okay, so let's take the water out. And instead, I'm going to put in Caro syrup after I get this extra water off here. In fact, let me get it focused a little bit just so we don't see the surrounding and just see the light that's coming through here. And I'm going to put Caro syrup in here, which I got yesterday at the Stop and Shop. It's the real thing. And it's very sticky. Okay. So far so good. Now watch this. It's a lot better with the room lights off, but we're having trouble with the room lights, and I'm not going to risk it. Okay, so the Caro syrup is doing something to the light that glass didn't do and water didn't do. And Caro syrup turns out to have molecules that are just one hand because it's like sugar. Remember, sugar is handy. Okay, so that phenomenon was discovered just a few years later by the rotation of light, it's called, by Jean-Baptiste Biot. And what does rotation mean? Well, I was rotating that thing, so that seemed to have something to do with it. But I'm going to show you another example, and for this one, we really do need it to be pretty dark to see it well, I think. I'm going to cover this up, and we need that light off back there. And I'm going to block this one off. Okay. And now here you see a green laser light. Can you see it going up through a tube that has sugar in it, that is, has Caro syrup in it. And does anybody notice anything about this green line? Can you see it? I'm looking at it against the dark, and I don't know. Can you see what's funny about the green line? Somebody tell me.
There's a moving thing.
It comes in little bits, right? There are dark areas of the line.
Oh, yeah.
Now, can anybody see that it's light some places and then dark and then light and then dark? Now, I want people to tell me where it's dark, right? Now, so everybody's not talking at the same time. I'm going to ask someone over on this side. Do I have a volunteer over there? Yeah, okay, I see it's just behind the aisle. And do I have a volunteer on this side?
Yes.
Okay, so the guy that said, yeah, you do well. And I'm going to hold, can you see this little light?
Yes.
And see the green at the same time? I want you to call out when I hit the center of the dark area. Okay? Call out when I hit the center of the dark area. I'll start at the bottom and start going up. And tell me when it's just, those two people call out. Tell me.
Dark.
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 Wait a second. Let me try again.
Dark.
Dark.
Now wait a second. How many agree with the guy over on my right over here? How many people agree with those? You guys say, I agree.
I agree.
How many agree with the guy on the left?
I agree.
Aha, this is stereo. People on this side agree with the guy on the right, and people on this side agree with the guy on the left. What's going on?
I agree with you.
Well, what's going on is that this light, the polarization of this light as it goes through the sugar, is rotating. Now we can get a little light back on the subject if somebody can get it. Is somebody else controlling it, or I need to do that? And it's like this. The direction of the pole, remember the light was field pushing electrons back and forth. Right? Now sometimes it's like it's twisted as it goes up this tube. Sometimes it's pushing this way, sometimes this way. So over here, tell me when you can't see the ribbon. At what height? Right there. Right? Over here, when can't you see the ribbon?
There.
Right? It's different places because it's twisting, and you're looking at it from different angles. Right? So that's the rotation of polarized light.
That's the electric field rotating?
The electric field, the vibrating electric field is rotating as it goes through sugar, but it doesn't rotate as it goes through water or through air. Right? And, let's see. Right, so remember how this got different colors? The reason is that different colors of light rotate different amounts. It's not diffraction, it's this rotation phenomenon that we saw. So the red rotates more than the green. So sometimes you see the red, sometimes you see the green or the blue.
That's not refraction?
No, well, it's this rotation, the phenomenon we're talking about. Okay, now I'll go back. So that's what BO discovered. Okay, now we're going to go about polarized light. We're going to go 40 years later to 1848. And to this guy, who was a young guy now. These previous guys, this is 40 years later, so they're as old as I am, ancient. Okay? In fact, this guy's supervisor was 1 year older than I am at this time. And this guy was only, as you can see, 26 years old. Much closer to you than he is to me. Okay, so he was trying to learn to be a scientist, and he was trying different kinds of science. He was trying crystallography, chemistry, and physics. And in 1848, he made some observations and wrote a paper, and the title of the paper was The Relations That Can Exist Among Crystalline Form, so that's crystallography, chemical composition, that's chemistry, and the direction of rotatory polarization. That's this phenomenon we talk about. It could rotate either to the right or it could rotate to the left as it goes up. So he was trying to tie these different disciplines together. So this is a picture of crystals. It has to do with crystals. So he starts with this. So look at figure 6 down here. And suppose that sharp edge, you sand it off to make a new face on the crystal, right? One that looks like that. So then you get others. And you see the one to the right of that has such faces. So let's look at this one, which is a crystal of a salt of tartaric acid. Tartar was stuff that came inside wine casks, so they could crystallize it, and they were dealing with it. That was a crystal he had of that stuff. And there you see blue, one of these faces. But notice the symmetry of the crystal. There's not just one face like that. There should be 4 of them, like that, right? Because if the crystal's to be symmetric. Okay, so there should be 4 such faces, and there are 4 such faces. But suppose you cut off that little edge to make a new tiny face up there, right? Now, how many of those should you have? You should have 4 of them on that end of the crystal and 4 of them on this end of the crystal. So there should be 8 of these in the salt of tartaric acid, or as Pasteur wrote in 1848, 250 years ago, or 150 years ago, I mean. The 8 F edges should be modified the same way. So he looked at it carefully, and he saw that's not true. It was always the same 4. Only 4 of them appeared on the crystal, those little facets. Right? Not all 8. But this didn't surprise him. You notice that they form a sort of a twist, right? From the faces on the left end to the faces on the right end. It twists, right? And that substance, tartaric acid, when you put it in water, rotates light, the same phenomenon we put there. So there was a rotation in the crystallography, and there was a rotation in the physics once you put it into water. Okay? Now, there was another salt you could get from wine, right? And it was called racemate, and it had the same chemical formula as the tartrate did. But the previous authority had reported that crystals of this compound, which don't do this trick of rotation when you put it in light, right? That they had the same shape as the tartrate. And Pasteur thought, that just can't be, right? Surely not. Shouldn't crystals from this untwisted version, if the molecules aren't twisted, then the crystal shouldn't be twisted either. Let me just put this down so it's not in your way here. So he went to look carefully at this one, thinking that now you should see all 8 because the molecules aren't twisted. They aren't doing this trick. Okay, and what he saw was really interesting. Right? That some of them looked exactly the same as tartrate, but others had the other 4 out of those 8. So some crystals looked like this, and other crystals looked like that. So what the heck did he figure was going on? So he separated the 2 that were twisted one way and twisted the other way and dissolved them in water to see what happened, right? And this is what he said. I carefully separated the right from the left crystals, and observing their dissolution separately with Monsieur Biot's polarization apparatus, I saw with surprise and delight that the right crystals turned the polarization to the right, and the left crystals turned the polarization to the left. Okay. So now he knew what was going on, that racemate was a mixture. Half of it was this other stuff, tartrate, that he'd already studied, and the other half was the mirror image of it. Right? So there were 2 kinds of molecules, and they were together in the crystal. That is, they were together in the sample of the crystal, but one crystal would be one and one crystal would be the other. So this was the first time that a chemist separated molecules that were mirror images from one another. This is chemistry's first purposeful separation of mirror image molecules. And you know, his teacher, Biot, who was old like me, right, didn't believe this could be true. So he had young Pasteur come and he supplied him the racemic acid. And he said, use my racemic acid, use my machine to measure this rotation, and do it in front of me. And it worked. So that was the first time that that had happened. So it showed that molecules somehow have a twist to them one way or the other. It could be mirror images. But what Pasteur found very soon was that he wasn't the only one that can do this. Microbes can do it too, because he took a mixture of the right-handed and the left-handed tartaric acid. That is, he took that racemic acid and he put yeast with it. And what happened was that the yeast grew, but it left the left-handed tartaric acid. It only ate one of them. So it left the other. So the yeast could separate them too, eat up one and leave the other one. Right? And this is very important nowadays because many drugs that are used in medicine are handed. And until about 20 years ago, they were always sold as a mixture of right and left. Right? And those things will behave differently, just like shaking hands is different right and left-handed. Right? And it turned out that one of them could be good for you and the other one a poison. Right? So they had, now such compounds are all made in one form so that they'll work properly. Okay. And this observation is what got Pasteur to be a microbiologist, to do pasteurization for milk and so on, was this study of microbes that he got into because he was studying chemistry and physics and crystallography. But it raised the question, then, once you knew that molecules were handed, what determined the chirality of life, whether it was right or left-handed? And Pasteur said, if the first principles of life are dissymmetric, that is, handed, they are, according to me, as one of the ties between life on the Earth's surface and the cosmos, that is to say, the set of forces spread throughout the universe. That is, there must be some force in the universe that determines it to be one hand and not the other hand. Now, in fact, there is such a force. It's called the weak force. But it's not called the weak force for nothing. It's really, really, really weak. And I don't think, there are very few chemists who believe it could do this trick. Right? So there probably is something else that does the handedness. Right? Now, it's not only in solution that things can rotate light. You can have crystals that rotate light. Like this bottle here is sodium chlorate, a salt. It has nothing to do with life. Right? And these are crystals grown from that. Right? But if you put them between cross polars, right, so no light gets through, the background is black, but some light is coming through the crystals. They're rotating it. But if you look, if you rotate those polars like I was doing here, you can see that there are two kinds of crystals there. Two of the crystals are right-handed and two are left-handed. So you can have it that way. And that is called optically active when it's able to do this trick of rotating light. Right? But this stuff, that salt, is not chiral when it's in solution. The molecules are not chiral, but the crystal is chiral. But that's not really too surprising that sodium chlorate in solution is not chiral, because chiral structures can be built from achiral units. You can take bricks, which are not right and left-handed, and make a right-handed or a left-handed helix. You can do the same thing with Legos that are not right and left-handed. Okay, now we're going to go 50 years into the future, into 1898, so a little more than 100 years ago. Right? And I'm going to ask you a question. Which hand, if you crystallize this stuff, sodium chlorate, which hand would you expect to get in your beaker? Now, I know that some of you are pretty young and have trouble thinking about things like this, and some of you are pretty old and have trouble thinking about things like this. Right? But let's just guess. Do you think you're more likely to get right or left or 50-50? How many people think right? How many people think left? How many people think you're most likely to get 50-50? That's by far, the democracy wins here. It should be 50-50. Okay, 50-50. I guessed that you were going to go that way. This was what Kipping and Pope thought a little over 100 years ago. So they wanted to test it, because that's what you do. You make a hypothesis, and then you test to see if it's that way. So there's Pope when he was a professor at Cambridge, but this time he was just a student. And here are the results. So he did 46 different beakers and grew crystals, and then he counted them, how many were the right-handed and how many were the left-handed. And he wrote down in this column how many right-handed there were, in this column how many left-handed there were, and he did it for 46 different experiments. So the total in those 46 crystallizations is what you expected. Out of 3,128 crystals, there were 1,562 right-handed and 1,566 left-handed, almost exactly 50-50. In fact, if you look at it there's where it is on the scale from 0 to 100% right. It's right at 50. And it's from, if you do statistics on this, you say it's plus or minus 1%. Right? So it's 50-50, which is what you said, so you were right. But now let's look at individual runs here. And this confirmed their hypothesis. They thought it would be 50-50. They wrote, the average product of a large number of crystallizations of sodium chlorate from water should consist of 50% of crystals of each hand. That's what they found. Now, let's look here in the third run, they got 64 right and 69 left. Right? So that's pretty good. Again, it's 50-50 within the error. And then let's look at this one. There's 24 to 68. That's not 50-50 with respect to the error. And here's one that's in the other direction. Right? And here's another one that's way off, and another one that's way off, and another one that's even further off. Right? So individual ones are not 50-50, but all over they're 50-50, which is what they wanted to find and what they found. Now there's an interesting lesson in this thing. Notice that that being not far off, you do statistics, would happen one time in 125 that you do it. It should be that far away from 50-50, right? And they did 46, so maybe they were just unlucky. You'd expect that in 125. 25 times you'd expect to get it. Maybe you got it within 46. But this one would happen only one time in 900, and that would happen only one time in 15,000. And this one would happen only one time in 250,000,000 at random. Would it be that far away? So this is not random, right? Obviously, there's some correlation within some of the runs, where if you have one hand, you tend to get that hand. Okay? But still, overall, they got very near 50-50. This is it. Only one time in 18 would you expect to get that close to 50-50. Now, maybe they were just lucky. Maybe that they lucked out that they were the one time in 18 when you would get that close to 50-50. But maybe not. Let's look. This is what they wrote. The experiments are numbered in the order in which they were performed. And in order further to eliminate personal bias, no calculations whatever were made until we considered that a sufficient number of experiments have been completed to ensure an accurate average. In fact, as little attention as possible was paid to the laboratory lists of data until the observations were concluded. Now this raises a question. Just how little attention can you pay to these numbers as you're measuring them? Right? They said they did a sufficient number of experiments. Well, they did 46 crystallizations, right? But why 46? And why 3,128 crystals? Why not do 50 experiments? Or why not 3,000 crystals and then stop? Well, since they did them in this order, we can see what would have happened if they had stopped after the first or the second or the third or the fourth or the fifth. We could see where they were going. So let's look at that. So here are the first ones, and they're very near 50-50. That's 0 on this thing. So they're very near 50-50. Okay, that looks good. And then suddenly this thing that would only happen one time in 250,000 occurred. Right? It took them way off. So they kept going. It got even worse, but then it started getting better. And then it got worse again. And then it started getting better and better. And now it's getting really good. Oh, goes away. But then it comes back. And there it's 1530 to 1530. Right? And they did one more, and it started going away, and they quit. Right? Now they were very honest people, I'm sure. But it's very hard when you're doing experiments not to put a bias in favor of what you expect to see. Very hard to avoid subconscious bias. Now, that same year, 1898, the subject came up at the annual meeting of the British Association for the Advancement of Science in Bristol, in England. And it was to take place in Colston Hall, which is shown here. But there was a problem. It was to start on September 9th. But actually, on September 1st, Colston Hall burned to the ground. And the venue for their place then looked like this on September 9th when they were supposed to begin. So they had to go someplace else. So the presidents, I've noticed, the lights are on the screen, but let's forget that because we don't want all the lights to go off. So Sir William Crookes was the president, and he was forced to deliver his presidential inaugural address, not in beautiful Colston Hall, but in a music hall at People's Palace. And this is what he said. I elect to speak on a still debatable subject, which does not yet enlist the interest of the majority of my scientific brothers. Confirmation of telepathic phenomena is afforded by many converging experiments. Now, some of you young people don't know what telepathy is. It's if I do thinking, you can you can understand my thinking without me saying anything or showing you anything, even if you're halfway around the world. And there are not many scientists now, and there are not many scientists there that believed there was anything then, that believed there was anything to that. But that's what the president of the Scientific Association is lecturing about. And there was a report on this in the famous science magazine Nature. Sir John Evans prophesied when introducing Sir William to the chair that the association would hear from him a remarkable address, and that prophecy has been amply justified. They got what they expected to get from Sir William, whose name, incidentally, is right on the front of this building. But this was not the meeting's most controversial topic. The most controversial was in chemistry, and was a lecture by Francis Japp, who was the president of the chemistry section. And his title was Stereochemistry, that is chirality, this handedness, and vitalism, that is the special stuff that happens with life. And he's delivered this talk at the Young Men's Christian Association. He said the contention of these chemists and others that now that we've discovered enzymes, we can understand everything in biology just in terms of chemistry. We don't need for special magic involving biology. It's all chemistry now. But, he says, this leaves intact the vitalistic origin of these phenomena. How did you get this one hand? That they're not answering. Right? No fortuitous concourse, he uses very fancy language here. No fortuitous concourse of atoms, even with all eternity for them to clash and combine in, could compass this feat of the formation of the first optically active compound. Coincidence is excluded, and every purely mechanical explanation of the phenomenon must necessarily fail. There must be something special, not like chemistry and biology. You can't just do it. I see no escape from the conclusion that at the moment when life first arose, a directive force came into play, a force of precisely the same character as that which enables the intelligent operator, by the exercise of his will, to select one crystallized enantiomer and reject its asymmetric opposite. That is, he thought there was some spirit in the universe that could choose the one. Okay? Certainly, if to argue the insufficiency of mechanical explanation is metaphysical, I must plead guilty. That is, he knew that scientists wouldn't like this. But he finds support for it in Newton's Principia. And let's not go into the Latin here, but essentially what Newton wrote was that there must be a being existing in order to make this happen. And he says he will merely add that that must be so, but the 19th century was not sympathetic to this kind of viewpoint. So within the next 3 months, 16 people wrote letters arguing about this in the magazine Nature. And Herbert Spencer, who thought up the idea of survival of the fittest, says that it seems to me that right and left could segregate. But it's not a question of right and left getting apart from one another. It's a question of choosing just one and not the other, so you don't have the other one. So he didn't understand what the problem was. Carl Pearson, who was a discoverer of many things in statistics, and also a rather sketchy idea called eugenics that we don't need to go into, said, I take it that a slight chance preponderance sets the breeding going. So chance, that's statistics, and breeding is what's involved in eugenics. So he was just trying to use words that had to do with his stuff. And he said if you put these mirror image things in a barrel and rotated it, he wouldn't be surprised to see that they went to opposite ends. That's amazing, but in fact, it's been patented. It evidently can work in some cases. And the physicist in Ireland, G.F. Fitzgerald, who's known in relativity circles because of thinking up Lorentz contraction before Lorentz, but was known locally in Dublin for being the first person to try to fly there. He said it must have started with just one, and that one must have been either a right hand or a left hand. And if everything else came from that one, then you could just get one hand. Or he said so it was controlled by the accidental symmetry, he said, of the first original crystal. Or he said the rotation of the sun in the heavens may be a sufficient cause, because the sun goes this way and not that way. That may be what was driven. So there were lots of ideas, but very little basis for deciding which should be which. Now we're going to go 50 years further ahead. No, actually, I'm going to do a little footnote about how crystals grow. You may have noticed my tie has a lot of crystals on it. So this guy in Germany said tiny pieces of salt dissolve more easily than large ones. Right? And then if you have a mixture of the two sides, the tiny ones will dissolve and the big ones will grow and you'll get all big ones. Right? And the reason for this is that if you have two crystals of different size with lots of little pieces in them, the ones on the inside are the happiest, the most stable. So the larger one has a higher fraction inside than the smaller one does. So it's more stable. The average molecule is more stable than a big one. So if you put it in solution so that molecules can come and go through the solution, they'll come off the little one and go on to the big one. So the idea is just that. Large crystals grow, small crystals dissolve. And therefore, getting that first crystal is a problem because it's going to start small, but small ones aren't stable. Have you ever heard of a joke, you can't get there from here? That's about trying to get crystals. You have to have small ones before big ones, and the small ones aren't stable. So how do you do it? So it's a hard thing to start growing crystals. So now we know we're worried about how do you do hands, and we know that small crystals will dissolve and big crystals will grow. We're going to try to put that together. So this guy in Holland in 1939 did an experiment with that compound, which has a mirror image, and they're in solution, and they go back and forth. Okay? But if you wait a while, you'll start crystallizing with just one crystal. Right? And it will start to grow, but it has to be just one hand, one or the other. And it drains everything over into that, and it all becomes one hand. So that's like what these guys were saying 50 years earlier. But he showed that it can actually happen. And I'll show you one other. If you stir when you crystallize, you can do funny things. This is a little stirring bar about that big in a solution, and there's nothing happening. And an hour later, you begin to see down in this corner, a crystal begins to appear. Just one crystal. And as time goes by, it goes out closer and closer to the stirrer. And finally, you'll see the stirrer hit the crystal. And when it hits it, it jumps a little bit. See it jump, 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 right? So for 15 seconds, it's hitting the crystal. But notice it's not knocking off any big pieces. The crystal is still there. But look what happens after we stop the stirring. And see how it's getting sort of grainy? The whole solution is getting sort of grainy. And if you look down in this corner, you'll see little flashes of light. And what that is light reflecting off new crystals. So for an hour and a quarter, there were only one crystal. But once that stirrer hits the crystal, suddenly there are 1,000 crystals in there. And they're all the same hand as the first crystal. So that was because of the problem of getting small crystals to get new crystals to grow. If you can knock tiny pieces, even ones you can't see, off pre-existing crystal, then all the new crystals will come from that. So in fact, even though there are thousands of crystals in there, they're all really one crystal. So they're all the same hand. Okay? Now, this bottle, which is a kilogram, does anybody know how many pounds a kilogram is? How many? How many is it? 2 pounds. 2 pounds of tiny crystals in here. Okay, and I bought that for not very much money. And I looked at it. And here's between the molars. And what you see is that of crystals from that bottle, of 77 initial crystals, only 2 were left-handed. So it was all one hand. So I got a real bargain when I bought this. If they could have charged a lot more money to have them all be the same hand, right? It's 94 plus or minus 2% excess of one hand, and no extra cost. So I was lucky. But see, what must have happened is when they made this stuff, they stirred it, and one crystal started, and they knocked all the others off that. So this is surely a case of secondary nucleation. Right? So again, having just one original crystal gives just one hand. That's fine, but this is never going to work if you start with a whole bunch of crystals, because then you have nuclei of all the hands, and you're never going to be able to get one. It's just not possible. Now we'll go 50 years from 1954, and we come to this paper, converting a polycrystalline mixture of sodium chlorate to a single hand by grinding. Now this isn't like the stirring where you start with one crystal. You're starting with a mixture of lots and lots of crystals. So how can you possibly do this? And I thought, there's no way that this works. I didn't know the guy who did it was in Spain, and I thought he must be a crummy scientist, and it's just not right. So I ignored it. And here's a picture of him. Cristallography is his name, and he's not even a chemist, he's a geologist in Madrid. And what he was interested in was whether the weak force would make it all be one hand. And no chemist believes that that could possibly work, but he's an amazing scientist, and he'll try things. So he tried it. He's a wizard. So he took 10 flasks and little stir bars in them, and 50-50 of right and left, and started them all stirring, put a little water in so they could stir them up, right? And then he got impatient, so after 10 days he went to look. Now, I think if any chemist thought it would work, there were no chemists who would think it would work. But if so, they would think it would take about 50 million years to happen, because the weak force is so weak. So, but he got impatient after 10 days, and he looked. And to the surprise of no one, they were 50-50 still, except for Flask 8. Flask 8 was 100% left-handed. And what he said was, if an experiment works, something has gone wrong. So try again. So he tried again, did the same thing again, and again, Flask 8 was 100% left-handed. Now, at this point, I would think that there's something biological in Flask 8 that's somehow doing this, although I wouldn't know what it is. Right? But he thought it might be what room they were in. So he changed room between Flask 2 and Flask 8 and tried again. And again, Flask 2 was 50-50 and Flask 8 was 100% L. And then he noticed something that I wouldn't have noticed. This is like Pasteur, who found that, looked at those little faces on the crystals to see things were right and left-handed. He looked at the stirrer that was in Flask 8 and saw it was different. It had a little ring around the middle. And he thought, it must be that it's wobbling as it stirs and grinding up the crystals. And that grinding is what's doing it. And here's where he was in luck, because he had lived on a commune, and he wore a bead necklace. And he thought, if I take the beads off my necklace and put them in there and stir it, it's going to grind much better than it did without the beads. So that's precisely what he did. He took the beads off his necklace and put them in there. And here's a picture of the flask with the beads from his necklace in it. And sure enough, in one day, it became all one hand. I didn't believe it. I dismissed this as obviously inconsistent with statistical mechanics. And Gibbs, who worked here at Yale 100 years ago, said that a mixture is going to be more stable than having just one. So it just can't happen. That's what I thought. But then some Dutch people, and together with some English people in 4 different labs, did the same kind of experiment, copying what he did with a different compound. And they found if they started with just a little more, 10% more of one right than left, it became, when they started to grind it with glass beads, after a week, it became 100%. Or if they started with a little less, it took a little longer, but it all went to 100%. And they started with mostly left-handed, it went to 100% left-handed. And it was, so it amplified whatever was in, even a little tiny excess would become 100% if you ground what they found. Right? And it got faster, it gets faster and faster the longer you go. Now, I got an email from the editor of Nature who said, do you find these observations convincing? And obviously I didn't originally, but these people I knew, the ones in England and in Holland. So I thought, yeah, it's convincing. And he asked if I would write a little article about it. And fortunately, I thought that. Because within a couple of years, all these other molecules did this, including down here on the right, this one, which is a drug that's sold for $6 billion a year. Of that is sold as a single hand. And normally people make a 50-50 mixture and throw half of it away. But here you can convert everything by grinding into one. So it's worth, you know, half of $6 billion a year. Maybe all of $6 billion a year. So the editor asked if I thought the paper was worth reporting in News and Views, and I said, yes, I do. But I have no idea how it works. So how can I write something if I don't know how it works? So it turned out there was a fellow in Japan who had published a complicated numerical simulation of this. Now, you know some math, but let me tell you that this kind of thing is really, really complicated. And the only way to do it is a computer. And even if you do it on a computer and it works, you don't know why it worked, right? So he got at something that worked, but he didn't know why. So that was the question, why? So I talked to a person who works in this building, John Tully, who's very good at theory. You can see plenty of equations written on his blackboard here. And we tried to figure out, why does that work? So we have a visualization of why it works. So suppose you have more of one than the other, right? And yeah, you put them in water and they start to dissolve and you get molecules in solution, but they go both ways. The molecules go back onto the crystal as well as off, right? And if you look at the red crystal, it looks just like one of the green crystals, right? So there's no selection, nothing that makes it better for a green than for a red. They look just the same. So the ratio shouldn't change, right? Now suppose we grind and knock off tiny pieces, but remember, tiny pieces will dissolve, right? So that's going to make dissolution faster. So more stuff will go into solution, right? But then again, more stuff will come from solution back onto the big crystals, right? So again, if you look at a red one and a green one, they look the same. And there's no bias that favors green over red. The ratio should stay the same. Now suppose we can have crystals grow by a completely different way that people haven't been thinking about. Suppose crystals could grow not only by molecules going onto a crystal one at a time, but by two crystals coming together. Right? And now if that happens, you're going to slow down. These tiny ones, remember, are going to dissolve. So they'll all dissolve, except some won't dissolve if they can come back and join the big one. Right? Then they'll be big. They won't dissolve. Right? But again, the right and the left look the same, except for one factor, which is this. There are two ways to save this green crystal. If you go onto this one, it can also go onto this one. And there's only one way to save the red crystal. So the little green ones are not as likely to dissolve as the little red ones are, because there are more ways to save them. Right? So the faster dissolution of this goes through solution and then comes onto here. Right? Now, this also can work as long as you have this select crystals growing this way, this selective attachment. Now I'm going to skip, it also happens, but I'm going to go through this quickly because time's going, if the molecules are chiral, like the molecules of light. Okay, so just a second here. So if you have this selective attachment, then this will work. So can we get any evidence that you do get crystals growing by two crystals coming together? And here is it. We take left-handed crystals of that stuff, sodium chlorate, and right-handed crystals that are dyed, and we mix them all together and put them in solution and shake them in water. And after that, they grow, and notice what's happened here. If I do that stuff with the polarized light, they've gone together with their own kind, except, as you see, there's one mistake up here. So it works, and therefore this must work. It must be that whatever, even if it's just a tiny, tiny excess, if you grind it, they'll all come the same. And it's not just grinding. It turns out that if you can take a boiling solution and they'll become all one hand too. Here's this same guy in Madrid that does crazy, crazy things. I took a bottle, put a little water and some of these crystals in and put them on a hot plate. So it was 120 degrees Celsius down here, 106 at the top. And after a while it started to snow because the solution came up and had dissolved stuff, gotten up to the top and cooled, and it made a lot of tiny crystals. And as they came down, the ones that there were more of got saved by coming together. So you don't have to grind, you can just boil and do it. Okay, so what process is the key? Is it grinding? No, you can do it without grinding. Shaking, you can do it without shaking. Boiling, reflux, turbulence, global formation, temperature gradient. The key thing is that you can get these crystals growing by coming together to save the tiny ones from dissolution. Okay, so the ripening, this process, is a possible source of the Earth's chirality, where stuff on the sand could have ground it, or it could have been, so I said the title of this was Did Life Grind to a Start? But it could be that it boiled to a start, that things started in Iceland in a geyser or something like that, where things were constantly boiling and you could enrich the one enantiomer. So remember at the beginning we said that Francis Japp said every purely mechanical explanation must fail. There's no way to do this, but that's not true. One of those letters in Nature, a fellow from Italy, Giorgio Nevada, said, in my opinion, the problem of spontaneous generation of life is not likely ever to be reduced to the far simpler question of the origin of molecular asymmetry. He was absolutely right. There's an easy way of doing it, just this grinding, but no one had thought of it for 200 years. And finally, this fellow here, Cristobal Viedma, working with his helpers here in Madrid, figured it out. And I'll show you a machine he invented. In fact, I'll show you not only this machine he invented to shake a sample, I'll show you the machine himself that he made for me. Now that thing did not cost $200,000. You know what it is? Where did this machine come from? On the bottom is a brick.
A blender.
And what's this part here that's doing the shaking? Anybody ever see such a thing? It's a sander. He bought it for $8. Right? So there's still lots of simple things you can do that no one has ever thought of. And so that it's wide open.